A space station with 1 million permanent residents would have to recycle almost everything they use every day for years. And even a system that recovers 98% of its water may not be good enough. NASA has already reached roughly that level aboard the International Space Station. Water from breath, sweat and urine can be cleaned and used again, instead of being thrown away after one pass. For a small crew supplied from Earth, that is an extraordinary achievement. Now, scale the same idea to a city of 1 million people. Suddenly, the missing 2% matters. So does every filter that wears out, every pump that fails, every contaminant that builds up, and every material the station cannot make for itself. A system that works brilliantly when Earth is nearby may look very different when an entire population depends on it, and replacement supplies are no longer guaranteed. And water is only the beginning. A city in space would need to keep people alive continuously, while thousands of connected systems depend on one another. Losing one capability might place pressure on several others, and the larger the population becomes, the less room there is for a failure to remain small. At some point, this stops being a very large spacecraft. It becomes a world. And that creates the real question: could we actually build a space station for 1 million people that could keep itself alive, or would some hidden limit appear long before we reached that scale? By the end of this video, you will understand what a 1 million-person space habitat would really require, where the hardest limits begin to appear, and what would have to change before a structure in space could stop behaving like a station supplied from Earth and start functioning as a world of its own. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. A 1 million permanent residents cannot be described by counting 1 million private homes. Homes cover the domestic part of life. Places to sleep, prepare food, wash, spend time together, and keep personal belongings. A settlement also needs civic spaces where shared decisions and public work can happen, clinical spaces for illness and injury, and educational spaces where children and adults can learn. Those aren't optional additions to the population. They are among the functions that make the population permanent. The same city ledger has to include work that residents may rarely see. Supplies need storage before anyone can use them, and freight needs places to arrive, wait, be sorted and move onward. Equipment needs maintenance while the settlement remains occupied. Emergency services need their own people, facilities and routes into whatever has gone wrong. Each function makes a different demand on the station, even before anyone decides how much space to give it or where it should go. An enclosure with homes but nowhere to handle freight or treat a serious illness has counted residents while leaving out part of their lives. That is why crowd capacity answers the wrong question. A structure might physically hold 1 million people for a limited event, and still fail as a place where they could live for decades. Permanent habitation includes days when people are healthy and supplies arrive as planned. But it must also include illness, damaged equipment, delayed work, and the continuing labor of keeping the settlement running. Empty volume says little about whether those activities can happen together. The capacity claim has to cover a connected city, rather than the maximum number of bodies that can fit inside a shell. A NASA settlement design study gives us the historical prompt for thinking this way. It treated a space settlement as an integrated system which helps turn the headline population into a catalogue of linked functions, but it is not a current reference design, and it does not show that a habitat for 1 million people can be built or sustained. It supplies no universal rule for how much habitat area each resident should receive, and it gives us no feasibility verdict for this station. At this point, the defensible result is narrower. Before choosing an exterior shape or assigning any area, the design must account for the domestic, civic, clinical, educational, storage, maintenance, freight, and emergency work of a city. The first entry can be a civic allowance of 500 square feet for each resident. That figure is an input to our comparison, chosen so the arithmetic can be followed. It is not a NASA requirement, an engineering result, or a promise that 500 square feet would give anyone a good life. We have not yet designed a station whose rooms add up to it. We are simply writing a stated allowance into the ledger instead of hiding one inside a finished picture. For 1 million residents, the multiplication gives 500 million square feet of non-farm civic floor area. Expressed another way, that is about 17.9 square miles of floor. The conversion does not mean the station needs a single deck covering 17.9 square miles. Floors might be arranged across many levels, divided among structures, or placed inside some other form. None of those choices has been made by this calculation, and the number alone tells us nothing about the volume around those floors or the density of people within it. The word civic also has to carry more than private apartments. People would need corridors and gathering places, schools and clinics, local storage, workshops, offices, and the service spaces that let those places operate. The card does not assign a separate fraction to each use, so we cannot pretend the allowance proves that every function fits comfortably. It gives all of them one transparent area claim that can later be tested, divided, or rejected. Several of the largest demands remain outside that claim. Food cultivation is separate, because growing space cannot vanish into the same headline figure used for homes and public life. Heavy utilities are separate as well. The large machinery and working areas that support air, water, power, waste handling, and other station systems still need their own entries. Reserve space also remains unassigned, rather than being treated as if every available floor can be occupied from the beginning. So the ledger now contains one limited quantity, 500 million square feet for non-farm civic use, based on a declared 500 square foot allowance per person. It does not guarantee comfort or feasibility, and it does not select the station's shape. What it does give us is an auditable claim, while the farms, heavy machinery, and reserve capacity are still waiting for physical room of their own. Reserve capacity cannot remain a blank line in that ledger. It has to become a set of places. Emergency circulation takes floor area, and so does the access needed to maintain and repair settlement systems. Those routes are part of the settlement itself. If they are counted only as corridors left after homes and public rooms have been assigned, their physical claim has disappeared, even though the work they support has not. That distinction changes how space is measured. A passage may exist on a plan and still be unavailable when people, stored material, or ongoing activity occupy it. A service area has little value if reaching it requires another part of the city to stop being used. Stores and working spaces need approaches that remain available while people continue living around them. So the allocation test cannot ask only whether every square foot has an occupant or a named purpose. It also has to ask whether the settlement can reach what it needs while that assigned space is in use. Maintenance makes this requirement especially clear. A system can have enough room around it on paper, yet the path there can compete with daily movement. Protecting access means claiming the route as deliberately as the destination. Emergency circulation cannot be promised simultaneously to another use and then expected to reappear during a local disruption. Reserve must remain reachable when another area is busy or unavailable. The city ledger needs a second view beside its allocation table, a reserve and compartment map. The table records how much area each function claims. The map records where protected routes run, where service access must stay open, and which areas could be separated from their neighbours. Together, they expose conflicts that a total would hide. Reserve in the wrong place may not support the area that needs it, while a separable area without a protected approach may be difficult to use during service work. This source does not tell us what fraction of the city to reserve, how many compartments to create, how quickly people must travel through them, or what emergency and evacuation rules should govern them. Those choices still have to be made. For now, the claim is narrower. Access, separation, and reserve each occupy real space, and the city's arrangement must keep that space available when daily use or a local disruption places pressure on it. Those spatial claims still do not draw the station. A ledger can tell us that circulation, separation, and reserve need room, then carry those claims into a later design. It cannot tell us whether that room belongs inside a ring, a cylinder, one broad deck, or some other exterior form. The settlement design study behind this comparison is an integrated systems prompt not a current reference architecture. It helps us keep several needs in view at once, but it does not supply a finished city that can simply be enlarged. Even the same stated floor allocation can take very different physical arrangements. It could be divided among more decks or fewer ones. The cross-section could change while the amount of floor assigned to residents and shared functions remained the same. Space could be concentrated in one part of a connected settlement, or distributed differently through it. Two proposals could therefore agree on every entry in the ledger, and still place those entries within unlike shapes. Choosing any one of those arrangements now would add an architectural decision that the ledger itself never made. A total area is therefore a constraint on a later design, not a hidden drawing of that design. The comparison does have one firm boundary. We are considering one connected settlement intended for 1 million permanent residents. That gives later physical comparisons a common subject. One population living permanently within one connected system. It does not prove that a ring, a cylinder, a stack of decks, or any other layout can support them. Nor does the boundary settle how densely people live, how much enclosed volume surrounds them, or how much structure the station would require. So the floor ledger can rule out an architecture that fails to provide the space already claimed for access, separation, and reserve. It cannot work in the opposite direction and select the architecture for us. No station diameter follows from it. No verdict about livability follows from it. And the historical study does not validate a design for a city of this size. The shape has to remain unresolved until a physical relation makes geometry explicit. And the next test begins with what residents would actually feel inside that geometry, the condition created when the settlement rotates. That added condition can be written as a simple mechanical relation. At a rotating habitat's rim, centripetal acceleration depends on its radius and how quickly it turns. In equation form, acceleration equals radius multiplied by angular speed squared. Measured in radians per second, angular speed connects the habitat's size directly to its rotation. For an illustration, the target acceleration can be set equal to standard gravity. That reference is exactly 9.80665 meters per second squared. It gives the calculation a declared value, rather than a vague request for Earth-like gravity. It does not mean that every part of a station must use that acceleration, or that this value has already been chosen for the settlement. It is simply the transparent reference for one guard arithmetic. With target acceleration fixed, radius and spin are no longer separate design choices. If the radius becomes smaller, the angular speed must rise enough to preserve the same product after that speed is squared. If the radius becomes larger, the same target can be reached with a lower angular speed. Rotations per minute are another way of stating that turning rate, so choosing a radius also constrains the required rotations per minute. You can picture the relation without choosing a station design. Mark a point on the rim and follow it as the habitat turns. Its direction of travel changes continuously, even if its speed around the circle stays steady. That continual change in direction requires an acceleration toward the center. Increase the turning rate and the inward acceleration rises with the square of that change. Increase the radius while keeping the turning rate fixed, and the acceleration at the rim rises in direct proportion to the added radius. A small ring is therefore a different rotational environment, not merely a scaled-down copy of a large ring. Preserving the same one target forces the smaller ring to turn faster. The equation can calculate that mechanical exchange before anyone decides whether a particular combination is acceptable for permanent residents. It cannot establish what rotation rate people would tolerate, what radius they should live within, or whether one chosen gravity level is suitable for long habitation. Those require evidence about human responses to artificial gravity. For now, the open architecture has one firm constraint. Target acceleration, radius, and spin must be chosen together. Set the target at 1g and choose 2 rotations per minute. The rotation relation then places the inhabited rim about 735 feet from the axis, roughly 0.14 miles. That distance is the radius, measured outward from the still center to the floor where a resident would stand. The result gives the selected acceleration at that floor. It does not say that 2 rotations per minute would feel comfortable or remain healthy over years. Now slow the ring to 1 rotation per minute while keeping the 1 G target. The required radius becomes about 2,940 feet, or 0.56 miles. Cutting the spin rate in half does not merely require twice the radius. Because the spin rate is squared in the rotation relation, the radius has to grow by a factor of 4 to preserve the same acceleration at the rim. Slower rotation has brought distance from the axis, and that distance has to exist as real structure. The whole city changes with it. If the occupied portion follows the rim, a 4 times larger radius gives that circular path 4 times as much length. Homes, farms, corridors, pipes, power lines, and emergency routes must be arranged around a much longer circuit. The structure also has to hold that larger ring together. A preference that sounded like a small adjustment to the rotation rate has therefore become a different construction and layout problem. This comparison remains an illustration, not a station design. Standard gravity supplies the 1 Ga premise, and the rotation relation supplies the 2 radii. Neither calculation establishes how people would respond to either spin rate, whether they would be comfortable, or whether 1 Ga is the right long-term target. It also does not validate the materials, shape, or internal plan of a ring built at either scale. What the calculation does settle is the geometry attached to the choice. At 2 rotations per minute, the illustrative rim sits about 0.14 miles from the axis. At 1 rotation per minute, it sits about 0.56 miles away. The slower case leaves much more room between the inhabited floor and the center, but it also makes the station far larger, and once people live across that distance, conditions cannot remain the same all the way from the rim toward the axis. That change begins as soon as you leave the rim. The Artificial Gravity Research Roadmap identifies gravity gradients as an unresolved design issue. A calculation for the outer inhabited floor tells us the acceleration at that radius, but it cannot describe every deck closer to the axis. The rotating settlement, therefore, contains a range of mechanical conditions. A person at the rim and a person farther inward would not occupy equivalent places simply because both are inside the same station. Moving between those places adds another problem. The roadmap treats translation through a rotating environment as its own operational concern. Travel toward the axis is more than a trip between 2 rooms with different addresses. It carries a person through changing conditions created by the station's rotation. The same applies in reverse on the way back toward the rim. A city built across that radial distance would have to treat the route itself as part of the habitat, because residents and supplies would repeatedly cross it rather than remain on one calculated floor. The roadmap also separates cross-coupled motion from that translation. Motion within a rotating environment can involve demands that the rim acceleration alone does not settle. So even after engineers choose a radius and rotation rate, they still have to study what movement inside the settlement requires. One successful number at the rim cannot answer how routine travel, physical work, or care should be carried out elsewhere in the structure. That reaches directly into the city plan. Housing placed close to the rim may occupy different mechanical conditions from workplaces, clinics, storage areas, or transport routes extending inward. Essential services cannot be assigned space as though every floor were interchangeable. Their location has to account for the conditions people meet while living there and while traveling to reach them. Care also has to remain reachable across that varied environment, while workers, patients, food, equipment, and waste move through it day after day. The roadmap does not give a tolerance threshold for those gradients. It does not provide a symptom rate, an acceptable travel rule, or a medical standard for permanent residence. Those limits cannot be filled in from the rim calculation. What it supports is narrower. Gradients, translation, and cross-coupled motion remain research and design concerns. The station's radius may establish the outside geometry, but human suitability depends on the changing interior that geometry creates. That changing interior is also why a successful rim calculation cannot become a medical answer. The artificial gravity roadmap still leaves a more basic question unresolved. How much gravity does a person need for health and performance? It also asks how long that level must be sustained. A rotating floor can create a candidate condition, but the geometry alone cannot supply either answer. Those questions have to stay separate from the convenient illustration of a station with a radius of about 0.56 miles, turning once each minute. That example describes a mechanical arrangement. It does not establish that the resulting condition will protect health, support performance, or remain suitable across the lives of many different residents. The calculation tells us what the floor can feel like under a chosen set of assumptions. It does not turn those assumptions into a universal prescription for artificial gravity. Rotation therefore brings an unfinished research program. Ground and shorter duration studies can help researchers examine motion-related effects and decide which conditions deserve further testing. But neither setting directly validates a rotating city as a place where people can live for entire lifetimes. A plausible radius and spin rate can be calculated now. Comfort, adaptation, medical care, and lifetime human suitability still require biomedical and operational evidence. So rotation remains a conditional physical setting inside the station design. Engineers may use it to define the candidate floor, its gradients, and the interior arrangements that follow, while treating human performance and long-term health as open requirements. Before anyone can call that setting habitable, another physical service has to work continuously around it. The station must hold pressure and keep breathable air reaching the people inside. Holding pressure begins with a simple distinction. A station can contain a great deal of air and still fail to provide a habitable pressure volume. The air has to be enclosed by a physical boundary that remains under control. In a rotating city, that means the structure around the candidate floor is doing more than carrying loads or defining rooms. It is part of life support. Every occupied space depends on that enclosure separating its internal environment from the space outside. Until the separation exists, the rotating floor is only a mechanical setting with air placed inside it, not a place that can continuously hold the conditions people need. The boundary also includes every route that crosses it. People need passages through the enclosure. Equipment may need openings large enough to move between sides, while services need their own paths into or out of the occupied volume. Each route has another job, but it must perform that job without giving up containment. A passage cannot be treated only as a way to move a person. A service path cannot be judged only by whether it carries what the city needs. Wherever the enclosure is crossed, that crossing becomes part of the pressure system. The city therefore has to treat its necessary penetrations with the same basic requirement as the surrounding structure. The defined environment on the inhabited side must remain bounded and controllable. Making the city larger does give it a larger inventory of air, but inventory and containment answer different questions. More air may mean that a given loss changes the total volume less quickly than it would in a smaller compartment. It does not turn an uncontrolled opening into a controlled boundary, and it does not make a breach a solved condition. The source behind this requirement does not tell us how thick the enclosure should be, what materials should form it, what pressure it should hold, or how many penetrations a city for 1 million people would require. It supports the system's boundary instead. Sustained habitation depends on containing pressure across the enclosure and its necessary crossings. Only after the city has a physically bounded environment does the next air question become meaningful. What, exactly, should that enclosed atmosphere contain, and how can its condition be maintained? The enclosed atmosphere has to meet a chemical specification. Oxygen may be present, yet that fact alone does not tell you whether the air is safe to breathe. ISO 16726 treats harmful chemical contaminants inside a spacecraft habitat as an air quality requirement. Safe occupancy therefore depends on controlling what remains mixed into the air, rather than assuming that a pressurized volume with oxygen is ready for people. The pressure boundary gives the air somewhere to stay. It does not establish the air's chemical condition. Carbon dioxide has its own stated limit. NASA's current requirement says that its 1-hour average partial pressure in the habitable volume must be no more than 3 millimeters of mercury. That is a measurement of carbon dioxide's contribution to the atmosphere's total pressure. It turns the gas into a monitored operating condition. The system has to know whether the average remains within the requirement over that hour. The value applies to the habitat. It is not a number that can simply be multiplied by 1 million to produce a design for the station. Air becomes breathable through continuing services that can sense chemical drift and remove what should not accumulate. A reading can show that carbon dioxide or another contaminant is moving away from its allowed condition, while removal brings the atmosphere back under control. Stored oxygen cannot perform either task by itself. It can supply one required gas, but it cannot detect an unwanted chemical or take that chemical out of circulation. Containment, sensing and removal therefore answer different parts of the same physical problem. That distinction also changes how a city-sized habitat has to be understood. The atmosphere is not one permanent batch that becomes safe when the doors close. Its condition can change within the bounded volume, including in a local area before the change reaches the rest of the station. Recognizing that change is part of maintaining breathable air, because a pressure reading alone would not reveal which chemicals were drifting. These requirements do not specify the ventilation rate, the kind or number of removal devices, the total gas inventory, or the staff needed for 1 million residents. They establish the narrower requirement beneath every such design choice. Air quality must be measured and controlled continuously, with local failure recognized before it spreads through the city. That local warning only helps if the station can tell where the change is happening. Sensor coverage has to distinguish an affected part of the occupied habitat from the areas around it. Fire response provisions have the same need. A leak, smoke, or contaminated air cannot be treated as though every room and passage has already reached the same condition. The first task is to locate the section that has changed. Once that section is known, compartment doors and isolation valves become part of environmental control. A closed door can separate the air and pressure in one compartment from the next. An isolation valve can cut the affected section away from services that would otherwise connect it to the wider habitat. Together, these interfaces let the station change its internal boundaries in response to the event, rather than leaving every occupied space joined to the same pressure and service network. The sequence is simple, though the machinery behind it may not be. Sensors identify the local condition, the response system determines which section is affected, and doors and valves separate that section from its surroundings. If the separation holds, a problem that could expose the entire city becomes a bounded problem while recovery is attempted. People outside the isolated area are no longer sharing the affected volume through every open connection. The fault still exists, but its immediate reach has been reduced. That reduction is what compartmentation buys: time and a smaller scope for the response. It does not seal a leak, remove contamination, extinguish every fire, or make damaged equipment work again. It keeps one local failure from immediately defining the atmosphere throughout the habitat. The separated section can remain unavailable while the rest of the pressure environment is protected from that direct connection. The available provisions do not tell us how large each section should be, how many sections a city for 1 million residents would need, or how quickly detection and isolation would occur. They also do not establish a fault probability, an evacuation capacity, or a guaranteed performance result. Any claim that the system buys time is therefore limited to the consequence of containing the affected volume. It is not a promise of survival. The city still needs enough operational capacity to make the damaged section safe and return it to service. That operational capacity begins with something much less dramatic than closing a pressure door. The affected equipment has to remain reachable. NASA's human system requirements include the access people need to operate and maintain habitation systems over time. Access, then, cannot be treated as a convenience to be added after the city has been built. It is part of whether the habitat can keep working. That changes how the walls, floors, service spaces, and installed machinery have to be understood. A pressure-dependent home is never complete merely because every section was intact on its first day. Its condition has to be inspected as the years pass. When work is required, crews must be able to reach the relevant system and repair it, without turning a hidden component into something that can be replaced only by opening up an occupied part of the city in an improvised way. The source requirements establish inspection and repair as continuing parts of sustained habitation, but they do not tell us what those jobs would look like in a rotating city of 1 million people. They give no repair time target, staffing level, spare parts inventory, work schedule, access route design, or demonstrated maintenance plan at that scale. We can say that the capability has to exist. We cannot claim that a particular crew arrangement or store of replacements would be enough. This is where sectional isolation reaches its limit. Closing off one affected volume can prevent a local air service problem from spreading directly into the rest of the pressure environment. Yet the closure only preserves a bounded problem. It does not inspect the failed service, operate the equipment needed to make the area safe, or return homes and workplaces to use. People still have to perform that work. If they cannot, the isolated section remains unavailable. The source does not support a specific chain of later failures, so there is no basis for inventing one. The narrower system's consequence is enough. Each section left out of service becomes another burden the settlement must carry, while supporting everyone elsewhere. Containment has bought time, but restoration decides whether the city recovers the space it lost. Across the settlement's lifetime, the pressure boundary is therefore an operating responsibility, sustained by repeated access, inspection, and repair. That same dependence on accessible, working hardware appears inside the water system. On the International Space Station, the Environmental Control and Life Support System has now reached a total water recovery milestone of 98%. The result came with the brine processor assembly, a specific piece of operating equipment added to a real life support system. Water recovery, then, is not merely something a future station might attempt. A crewed spacecraft has demonstrated it while people were living aboard. Before the brine processor assembly reached that milestone, the station's total water recovery stood at about 93 to 94%. The increase came from hardware operating within the station's existing recovery system and retrieving more water from its waste stream. The improvement was only a few percentage points, but those points represent the difference between water returned for use and water that still has to be replaced. This is the strongest lesson the station can give us here. Recovery performance can improve when engineers identify a remaining loss and build equipment that works on it. The International Space Station provides a bounded operating example, one defined system, serving a limited crew under known conditions with support beyond the station itself. Within those limits, the change from roughly 93 or 94% to 98% is a measured advance, not a prediction. But 98% recovery is still different from a closed water supply for a permanent city. The figure does not show loss-free operation, and it does not tell us that the same equipment could support 1 million people for decades. It also says nothing by itself about how often parts need attention, what replacement hardware must arrive from outside, or whether the system could keep meeting that benchmark without external support. Those questions sit outside what this result demonstrates. So the benchmark gives the city something firm to begin with. Very high recovery has been achieved in working spaceflight hardware, and a particular machine raised the previous result. It also leaves a small unrecovered share and an operating system that must continue to function. Once a water loop becomes this efficient, the next calculation is no longer whether recycling can work. It is how the remaining loss, maintenance burden, and operating conditions accumulate when the crew becomes a city. A recovery figure of 98% still describes a loop with an exit. For every amount that passes through the process, most returns for use, while a small share does not. The percentage can make that missing share sound harmless, especially beside the much larger amount recovered. But the recovered water goes around again. The missing water does not. A settlement, therefore, has to treat it as a continuing subtraction from a limited stock, without pretending that the available result tells us how quickly that stock would fall. That subtraction creates a separate need for makeup water. High recovery can reduce how much makeup material the settlement must provide, but it cannot reduce the requirement to zero while any residual stream remains. The source does not give us a depletion clock for a city of 1 million people, or an amount that must be delivered on any schedule. It supports the simpler operational point, a loop that returns less than everything needs some material held outside the loop to replace what is lost. The recovery percentage also belongs to working equipment. Water does not return merely because the pipes form a loop. The system has to keep processing it, which makes its hardware and replacement components part of the water supply. If a component is unavailable during maintenance or after a fault, stored water and functioning recovery equipment are no longer interchangeable entries. One is the material the population can use, the other is what allows used material to become available again. The change from about 93 or 94% total recovery to 98% makes this dependence clearer. Recovery improved when the system changed. It is engineered performance, not a permanent feature attached to water use. That result demonstrates what particular spaceflight hardware achieved. It does not provide a failure rate, a service interval, or proof that the same performance would continue without outside support. So the permanent ledger needs several separate lines. There is water circulating through the settlement, make-up material for the fraction that does not return, replacement components that keep recovery operating, and a protected reserve for periods when equipment is being worked on or is unavailable. The exact size of those holdings cannot be taken from the International Space Station result. Their existence follows from the limits it leaves in place. Recovery is incomplete, and it depends on machinery. That permanent ledger cannot begin with a citywide total, because the available individual figure answers a much narrower question. NASA uses an allocation of 2.5 litres of potable water per person each day. That is a drinking water baseline for one human being. It is not a complete allowance for everything that person needs from a settlement's water system, and multiplying it by 1 million would give only the potable line, not the station's entire water requirement. Sustained habitation joins water to a larger set of functions that also includes food, contaminant control, waste handling, and the conditions that keep living spaces usable. Those functions meet inside the same settlement, but they do not place one interchangeable demand on water. Water that reaches a person as a drink has one purpose. Water committed to growing food, carrying away waste, or maintaining a habitable environment belongs to other services, even when a recovery system later returns some of it to a shared inventory. So the station's plan has to declare those services separately. Hygiene needs its own demand. Crop production needs another. Fire response must have water available for an event that may never occur, while medical care must be supplied when people are ill or injured. Industrial work also draws from the inventory, and an emergency reserve has to remain protected rather than being treated as spare water for daily use. Putting all of them under the drinking allowance would hide which service is consuming water, which is holding it ready, and which could be interrupted when equipment fails. The sources do not tell us how large any of those city-scale allocations should be. They provide no crop water budget, no fire water quantity, no municipal rate per person, and no storage calculation for 1 million residents. Those values would depend on the station's architecture, what it grows, which processes use water, how each stream is collected, and which users can tolerate delay. Recovery links the streams, but it does not erase their different jobs. A credible inventory, therefore, has several declared demands sharing one managed supply, along with the make-up water, machinery, and reserve already required by incomplete recovery. Only after the services are defined can designers ask how much water the station must hold, how quickly it must move, and what portion has to remain protected. Water becomes even harder to count once those separate demands join the rest of the station's living machinery. The European Space Agency's Melissa concept treats water as part of a regenerative life support system linked with carbon, food, oxygen, and waste. Water passes through processes that affect the other flows, while waste from one process may become material for another. That is a concept for connected biological and chemical pathways, though not proof that a city of 1 million people can close every loop. Losses, reserves, service demands, and recovery limits still remain on their own ledgers. The water held in reserve may carry another consequence. A stored body of water has thermal mass, so changes in its amount or location can matter to the station's thermal behavior. This follows from placing water inside a linked system, rather than treating it only as a drink delivered to residents. Yet the reserve cannot be assigned twice. If some of it moves into a life support process, the thermal inventory has changed. If operators protect a portion against contamination or equipment failure, That portion may no longer be available on demand elsewhere. The thermal role is therefore a systems inference tied to where the water is held and what the life support system is doing with it, not a claim that a tank disposes of the station's heat. Water can enter a third ledger because it is rich in hydrogen. Radiation analysis can evaluate hydrogen-rich materials, including water, as shielding. Whether a given store provides useful protection depends on the radiation environment and on geometry, where the water sits, what lies behind it, and which directions the exposure comes from. A reserve tank somewhere in the station does not automatically protect the people or machinery elsewhere, nor does describing water as possible shielding establish how much would be required. So moving one body of water can alter several branches of the design. Consuming it changes the life support inventory. Reserving it can change the available thermal mass. Placing it around an occupied region may give it a protection role, but only within that stated arrangement. Each effect has to remain visible, with no single gallon credited as though it were fully available for every job at once. And among the connected demands, the largest visible allocation still belongs to the branch that must grow food. That food branch begins with a change in what the plants are there to do. A few leaves in a cabin can make the room feel more comfortable, but a farm for a large population has a defined life support job. Its crops have to produce food that people can depend on over and over as part of the habitat's daily operation. The growing area therefore needs its own physical allocation. It cannot be treated as decoration fitted into whatever space remains after the rest of the station has been designed. The same crops can also take part in the exchange of gases inside the habitat. As they grow, plants can remove carbon dioxide and contribute oxygen. That connects cultivation to the air system, but it does not make the farm a complete air system by itself. Its contribution depends on the biological process continuing, while the people, machines, and other living things keep adding their own demands to the shared atmosphere. Food production and air management meet at the crop, even though each still has to be accounted for clearly. Water creates another connection. Crop cultivation can be built into wastewater recycling pathways, allowing recovered water to return to food production, rather than treating every use as an isolated trip from storage to disposal. Once that link is made, the farm becomes one place where water, gases, and food pass through the same living process. A change in cultivation can then affect several life support exchanges at once. The plants are operating equipment in a biological form, with inputs that must arrive and outputs that must remain dependable. That is much more demanding than showing that a plant can grow during a flight or in a simulated space environment. Those experiments provide evidence that parts of biological life support can work under limited conditions. They do not demonstrate a complete, reliable diet for a city, an autonomous closed loop, or an operating farm for 1 million people. The gap is important because a small, successful crop can prove a biological possibility without proving the scale, variety, continuity, and reliability required to feed an entire population. So the farm has to appear in the station's inventory as a separate life support function, with an explicit surface and an explicit process allocation. Small plant experiments cannot supply that missing allocation. Ground-based studies give us a starting estimate for that missing allocation. A complete diet grown from high-light crops requires roughly 40 to 50 square meters of crop area for each person. In the units we have been using, that is about 430 to 540 square feet per resident. The estimate gives the food system a measurable physical demand instead of leaving the farm as an undefined box somewhere inside the station. For 1 million residents, the multiplication is direct. 40 to 50 square meters per person becomes 40 million to 50 million square meters of growing surface. Converted into square miles, that is about 15.4 to 19.3 square miles. Even the lower end is no longer a spare room attached to a habitat. The crops alone claim an area measured on the scale of a city. The farm cannot be assigned whatever space remains after the habitat is designed. That range still does not describe the full farm. The cited ground studies estimate highlight cultivation area per person. They do not predict the final footprint of an orbital agricultural system. Service corridors would have to let people or machines reach the growing areas. Equipment would occupy additional room around them, and reserve capacity would need its own allocation if the food supply were expected to continue when part of the farm was unavailable. None of those spaces is included in the 15.4 to 19.3 square miles, so adding them would increase the engineered farm area beyond the crop surface itself. Nor does the estimate choose the crops, settle their yield in orbit, or specify a layout. It does not tell us how many levels the farm should use, how much light each level would demand, or what productivity the finished system would achieve. Those are later engineering decisions. What the multiplication does establish is the scale of the cultivation claim before those decisions begin. Feeding 1 million people with a complete high-light diet requires tens of millions of square meters of active growing surface. The farm now has to compete for station area as a major life support system, while every corridor, machine, and reserve growing section remains to be added around it. That growing surface is only the part of the farm where the plants are visible. Behind it sits a process plant. Water has to reach roots in the right condition, nutrients have to move through the system, and whatever leaves the growing area has to be handled before it can become a dependable meal. A large patch of healthy leaves can still belong to a food system that fails somewhere beyond the light. Some of those jobs can be linked. Crop systems and photobioreactors can produce edible biomass while taking part in air revitalization, water treatment, and waste processing. Material leaving one process may become an input to another, so the farm is tied into the station's life support, rather than operating as a separate room full of plants. That coupling can reduce the need to treat every flow in isolation, but it also means the useful output depends on more than growth alone. Inside a photobioreactor, gases must pass between a liquid and the surrounding system. How that exchange behaves can change biological performance. The organisms in the liquid respond to their environment, and microbes elsewhere in the process respond as well. Change the process conditions, and their activity can change with them. A system that worked under one set of conditions cannot simply be assumed to behave the same way after its gas flow, liquid behavior, or biological population shifts. Nutrients follow the same logic. They have to be supplied, recovered, and kept in forms the intended organisms can use, while waste pathways remain controlled. The source evidence supports these connections, but it does not show that every nutrient can be closed into a complete loop. It also does not establish autonomous operation, a complete human diet, or dependable transfer to a city-sized station from pilot, ground, or flight systems. Food safety therefore belongs inside daily operation. Edible biomass must remain separate from unsafe material as water, nutrients, waste, organisms, and microbes move through connected equipment. Sanitation and process control are part of producing the meal, not work added after cultivation is finished. The assigned crop area tells us how much growing surface may be needed. It cannot tell us whether that surface will keep delivering safe food, because reliability now depends on the whole chain around it. A farm that works today does not become a fixed source of food simply because its equipment has been installed. Its output still depends on the conditions around the crop and on every process that carries water, nutrients, waste, and edible material through the system. If those conditions drift, the biological response can drift with them. The amount of growing surface may stay exactly the same, while the amount of safe food coming from it changes. That makes a failed harvest more than a shortfall at the final collection point. Crop disease may affect part of the growing system, while a sanitation problem may make food or equipment unsafe even when plants continue to grow. The affected area has to be separated before the problem spreads through connected processes. Recovery then means more than planting again. The food system has to restore controlled operation and safe production before that section can be trusted to feed people. None of the assigned evidence tells us how often such a failure would happen on a station of 1 million people. It also gives us no fixed recovery time or reserve period. Those values would have to come from a more detailed design, but their absence does not remove the design task. Isolation, recovery, and food held outside the affected process have to be considered before the farm can be treated as dependable. One response is to grow less of the diet inside the station. imported food, or a mixed system that combines cultivation with stored supplies, can reduce the internal surface committed to crops. That choice moves part of the burden elsewhere. Food must arrive through a logistics chain, and enough must remain in storage when a delivery is delayed or cultivation falls below demand. The available sources do not set an import schedule or say how large that reserve should be. Growing everything inside the station moves the burden back toward the farm. More food independence then depends on keeping a vulnerable biological process productive and on restoring it after disruption. A mixed system accepts more dependence on transport and stored inventory in exchange for less cultivation surface. Either way, food remains a continuous operational demand. Process control, sanitation, isolation equipment, recovery work, and storage all have to keep functioning when the harvest does not proceed as intended. Those loads cannot simply pause while the crops recover. That means the station's power supply has to support more than an average. The farm, air circulation, water treatment, sanitation, cold storage, and isolation equipment all draw power while other systems are being repaired. Sunlight near Earth may seem abundant enough to answer that demand, but the first number in a solar calculation describes the light arriving at the station before the station has made electricity from it. Near Earth, total solar irradiance is about 1,361 watts per square meter. Irradiance tells us how much solar power reaches an area. In this reference, that area faces directly into the incoming beam, so the sunlight strikes it squarely. It is a measure of the incident light. It is not a reading from a solar panel, a cable, or an outlet inside the habitat, and it cannot yet be counted against the farm's load. The direction of the surface changes what it receives. A surface held normal to the beam presents its full area to the sunlight. Turn that surface away, and the array presents less effective area to the incoming light. A station cannot treat its panels as though they always face the sun. Orientation has to be managed, and the amount reaching the array varies over time. Even a favorable orbit can improve collection only within those conditions. It does not make the beam constant at every collecting surface. That reference value also tells us nothing about how much panel area the station has, how efficiently those panels convert light, or how long the available sunlight can be collected. The sources do not choose a solar array, an orbital duty cycle, a mixture of power sources, or an allowance for each resident. Assigning those values would turn an environmental measurement into a city design that has not been established. So the solar figure belongs at the entrance to the power system. Light must first fall on a properly oriented collecting area, then be converted into electricity. The resulting supply still has to remain available as the sunlight changes, reach equipment through a delivery network, and support loads that cannot wait for better illumination. Storage and reliability, therefore, remain separate design problems. Before even one pump or lamp can claim a share, the station has to carry that incoming beam through every stage between sunlight and usable electrical service. The collecting surface is only the first working part of that chain. Sunlight arrives as environmental input, while a pump, lamp, or control system needs electrical power in a form that can reach it. Conversion connects those two conditions. Transmission then carries the converted electricity away from the generation side and toward the places where the station can put it to work. Until both steps have happened, incident sunlight has not become power at the equipment. Time separates those steps as well. Available sunlight can change while demand continues on its own schedule. A resident may need light when the input is lower, and a pump may need power without waiting for the collecting conditions to improve. Whenever the timing of supply and demand fails to match, some of the converted energy has to be stored while it is available and released when the load calls for it. Storage therefore carries electricity across a mismatch in time. The source establishes that need, but it does not tell us what storage method a station should use, how much it should hold, or how the city should arrange it. Once electricity has been converted, carried through any mismatch, and made available at the required time, it still has to move through distribution to the equipment that consumes it. Generation and storage sit on one side of this path. The station's loads sit on the other. Distribution is the connection between them during normal service. It lets electrical supply become ventilation, lighting, pumping, computing, or whatever other work the connected equipment performs. Those examples name demands on the path, not an allowance for each person or a chosen design for the network. That is why a generation figure cannot be read as a delivered service figure. It describes electricity at one stage of a longer system, before the full path to the load has been accounted for. The path includes conversion from incident energy, transmission away from generation, storage when availability and demand occur at different times, and distribution at the moment equipment needs power. None of that decides a transmission voltage, component count, storage technology, or distribution layout. It only defines what successful delivery means. Electrical power has traveled from the environmental source through the required time shift to a load that can use it. With that path clear, the next decision is which loads cannot tolerate an interruption. The first protected load would be the one that keeps the atmosphere safe to breathe. Air does not remain suitable merely because the walls hold it in. Its condition has to be monitored, and removal equipment has to keep taking unwanted material out. If either service disappears during an electrical fault, the power still being generated elsewhere says little about conditions in occupied rooms. Water creates the same dependency. Processing equipment has to keep water moving through the maintained environment, while food production needs continuing service of its own. Both are loads on the electrical network, and losing their supply can change what the population has available to drink or eat. The sources establish those connections without giving a power requirement or reserve time for either service. Mobility belongs in the decision as well. Access between working areas depends on equipment receiving power when people and materials need to move. Manufacturing also depends on continued service, where the station relies on maintained equipment and replacement work. A fault leaving generation connected to the wrong places could still separate people from a needed area or stop work supporting another system. Thermal pumps add another direct link between electricity and the occupied environment. They help maintain acceptable conditions, so their interruption does more than remove a convenience. Yet the evidence provides no finished ranking among air control, water processing, food production, mobility, manufacturing, and thermal pumping. It supports identifying and protecting these services before claiming the station could operate through failure. That changes what a generator capacity figure can prove. A large total may describe production or the network is healthy, but resilience depends on what remains connected when a component or path fails. Operators would have to distinguish loads whose interruption changes occupied conditions from those that can wait, then protect paths serving the first group. Until that hierarchy exists, spare generation is only potential supply. It does not prove that air, water, food systems, access, repair work, and temperature control remain available together. The sources stop short of a load shed table, a megawatt allocation, a reserve duration, or a complete operating doctrine for 1 million people. They establish the test a local grid must pass. A fault in one place cannot be allowed to remove every service that keeps the city habitable. That means the grid has to do more than deliver enough power while every path is working. Occupied rooms need controlled air, temperature, water, and other environmental services continuously. Establishing those conditions at startup proves little about the hour after a fault. The equipment has to keep operating, and the electrical network has to keep supplying the protected functions. A spare generator cannot do that by itself. If one electrical fault can spread through every route serving the station, additional generation may still sit on the wrong side of the failure. The recovery capability comes from separating the suspect section from the sections that can still operate. One zone may lose a path, while another continues receiving power for its protected services. It no longer gets to decide the condition of the entire inhabited station. That separation also changes what operators can do next. Instead of treating the grid as one inseparable machine, they can keep service in an unaffected area while work begins on the isolated one. This depends on access. Controls, interfaces, and damaged equipment have to remain reachable for operation, inspection, and repair. A component that exists on a diagram but cannot be approached safely does not offer much help during recovery. Isolation buys a working boundary, Reachable maintenance determines whether the failed section can return to service. The approved evidence does not tell us how many sections such a station should have, how they should be connected, or whether switching would be automatic or manual. It gives no outage length, restoration time, or proof that a particular design would work for 1 million residents. Those choices would depend on engineering that has not been specified here. What the evidence does support is the operating principle. Occupied conditions need continuing control, maintenance access belongs inside the service design, and local isolation can preserve service elsewhere while repair is underway. So redundancy includes a way to contain damage, continue supplying protected loads beyond it, and bring the separated path back when the work is complete. Power then behaves less like one station-wide promise, and more like a service that can fail locally and recover locally. Yet every section that keeps air moving, water circulating, equipment running, and rooms controlled turns electrical energy into heat. Keeping the grid alive only moves that energy into the station, where another system must carry it away. That last step changes what it means to keep the power on. Space may be cold, but a vacuum does not surround the station with cold air. There is no atmosphere brushing past the hull, warming as it goes and carrying the station's heat away by convection. The cooling process familiar from air moving across your skin cannot work outside a sealed habitat when there is no surrounding air to do the carrying. Heat can still leave, but its final route into space is thermal radiation. Energy must reach external surfaces that can emit it outward. Those surfaces are therefore part of the station's life-supporting machinery, even though they sit at the far end of systems that begin inside homes, farms, workshops, and utility spaces. Keeping a room comfortable is no longer only a question of moving heat away from that room. The heat must continue through the station until a radiating surface can release it into space. The people inside add to that flow simply by being alive. Metabolism releases heat into the habitat, while lights, pumps, computers, and other electrical equipment eventually leave energy behind as waste heat as they operate. Recovering power after a local fault keeps those services available, but every service that resumes also restores its contribution to the thermal load. A successful electrical grid can distribute energy to where it is needed. It cannot make the resulting heat disappear. That does not mean every unit of energy follows one identical path. Heat may begin in people or in different pieces of equipment, and the card's evidence does not specify the internal route each contribution takes before reaching an exterior surface. It also gives no total heat load for a city of 1 million people, no required radiating area, and no proof that a station at that scale could close its thermal balance. Those answers depend on the actual habitat, its equipment, and the stated performance of its radiating surfaces. What the physics does require is an unbroken path outward. If occupied spaces and equipment keep producing heat, the station must collect that heat, move it to suitable external surfaces, and radiate it away at the rate needed to prevent accumulation. Power may be restored section by section, but heat rejection remains a compulsory export from the habitat as a whole. For that final transfer, thermal control work uses the Stefan-Boltzmann relation. It describes how much thermal radiation a surface emits, linking the outgoing power to the surface area, its temperature, and its emissivity. Once those properties are stated, the relation gives an emitted power for each square meter. The station's heat burden can then be translated into the area of radiating surface that would be needed under those same conditions. Take an idealized radiator held at 300 Kelvin with an emissivity of 0.9. Before accounting for anything around it, each square meter emits about 413 watts. That figure gives the calculation a physical scale. A heat load is measured in watts, and the radiator supplies a certain number of emitted watts per square meter, so the required area follows from comparing one with the other. More heat requires more emitting area if the surface conditions stay fixed. But the surface conditions do not disappear from the answer. Temperature changes the rate at which the radiator emits, so a design operating at a different temperature will not retain the same output per square meter. Emissivity changes it too. A surface with a different emissivity does not radiate like the 0.9 example, even if its temperature and area are unchanged. Those choices have to be present before the area calculation has a definite meaning. The surroundings also affect what the radiator can accomplish. External heat absorbed by the surface adds to what it must handle, reducing the capacity available for rejecting heat from inside the habitat. Its view to space counts as well. A surface cannot be treated as though every direction offers the same radiative escape when part of that view is occupied by something that changes the exchange. The ideal emitted figure describes the surface alone before those environmental effects are included. So 413 watts per square meter is an example of emitted flux under stated ideal conditions, not a flight-ready promise of cooling performance. The approved evidence does not choose a radiator temperature, coating, fluid loop, geometry, or environmental margin for this station. Until those design choices and surroundings are known, radiator area can be estimated only conditionally. For this much heat, at this temperature and emissivity, with this absorbed heat and this view to space, the emitting surface must be this large. Take that conditional relation and give it one large, round heat load, 1 gigawatt. Under the same ideal assumptions, with the radiator at 300 Kelvin and its emissivity at 0.9, the area comes to about 0.93 square miles of one-sided emitting surface. That is the side which can radiate effectively into its surroundings. The figure turns a quantity of heat that is hard to feel into an exterior area that can be seen as part of the station. The gigawatt is only a ruler for scale. It has not been established as the amount of power used by a city of 1 million people, nor as the amount of waste heat their station would have to reject, and 0.93 square miles is therefore not a prediction of the station's required radiator area. It is the result of asking one tightly bounded question. If 1 gigawatt had to leave through a surface behaving according to those stated ideal conditions, how much one-sided emitting area would the relation imply? Nor does that answer describe a ready-made radiator. The calculation treats emitting area as an ideal quantity, while an installed system has to work in an environment and inside a physical design. Its actual performance would depend on the temperature engineers choose, the exposure each surface has to space, and the environmental conditions that alter the exchange. A surface that cannot radiate as assumed cannot simply be counted at the ideal rate. Any real design would also need margin beyond the area given by the relation, because the ideal figure does not include every condition that the built system must tolerate. So the visible consequence is larger than a number on a thermal worksheet. Whatever area the final assumptions produce has to be arranged around the station as working hardware. Its geometry must give the emitting surfaces the exposure they need, while the design must also accommodate plumbing, protection, and access for service. The 1 gigawatt example does not choose any of those solutions. It gives the designers a disciplined comparison. A stated heat load, temperature, and emissivity lead to a stated ideal area, and every real constraint must then be added without pretending that the first number was the finished radiator. That exposure is part of the radiator's job. A surface can release thermal radiation only if it has a usable view to space. If another part of the station blocks that view, some of the area counted on the worksheet can no longer perform under the assumed conditions. The radiator's position and orientation therefore belong in the station layout from the start, rather than in exterior space left after other systems have claimed a place. The surrounding environment can change the calculation as well. Sunlight absorbed by the radiator adds heat to a surface that is supposed to export it. Contamination can alter its thermal performance, so a panel that still looks like the same geometric area may no longer behave like the surface assumed in the estimate. The evidence establishes those sensitivities, though it does not specify a preferred temperature, working fluid, panel shape, or method for managing sunlight. Those choices would need their own design evidence. Once the radiating surface has a location, the heat must reach it. Plumbing has to run between the station's heat sources and the exposed hardware, passing through a structure already carrying air, water, power, people, and other equipment. Longer or more difficult routes are not free additions to a diagram. They occupy interior paths, cross structural boundaries, and create places that workers may eventually need to reach. Access changes the exterior plan too. A surface exposed to space still has to be inspected and, if its performance falls or a section fails, repaired or isolated. Nearby structures can cast shadows across possible locations, while competing exterior systems may need clear directions of their own. Designers would have to leave service routes and decide how the station continues exporting heat when part of the system is unavailable. The approved evidence does not choose a redundancy level, a maintenance interval, or a shadow control scheme, so none can be treated as settled. Heat export has now claimed more than emitting area. It has claimed open lines towards space, routes through the inhabited structure, reachable exterior hardware, and room for failures to be handled. Every one of those claims competes with something else in a station built for 1 million people. Before anyone can select a final arrangement, the thermal system has to be fitted into the same limited geometry as power equipment, living space, transport paths, and the outer structures that protect the population. The outer structure has another job competing for that limited geometry. It must help protect the people inside from radiation. Yet the word radiation can make the danger sound uniform, as though everything arriving from space posed the same threat. A habitat encounters different kinds of particles across different ranges of energy. Those differences belong at the beginning of the design problem, because one broad label cannot tell an engineer what is reaching the station. The wall does not respond according to thickness alone. Its material composition matters too. Change what the wall is made from, and you change how incoming particles interact with it. So two barriers with the same thickness cannot simply be treated as equivalent protection, while adding more material does not by itself answer what that material will do when particular particles arrive. Before anyone can judge a shielding claim, they need both sides of the encounter, the particle environment outside and the material response inside the barrier. Even that encounter cannot be defined once for every possible station. Orbit changes the environment in which the settlement operates. Solar activity changes it as well. A protection scheme evaluated for one location and one set of solar conditions therefore cannot be carried over to every other orbital settlement, without first defining the new exposure context. Where the station travels and what the Sun is doing during its mission shape the problem that its shielding must address. This leaves no source-backed universal thickness that can be placed on a drawing and called safe. The approved evidence also gives no single dose limit or exposure target for a permanent habitat, and it does not identify one material as adequate everywhere. Those decisions would require a defined mission context and an agreed protection target before the structure could be evaluated against them. Radiation protection is therefore part of the station's material accounting, but it begins earlier than a request for a thicker shell. Designers first have to describe what can arrive, across which energies, in the orbit and solar conditions the settlement will face. Then they can ask what each proposed material does in that environment and how much of it the structure can carry. Only after those questions are tied together can a wall be assessed as protection rather than treated as a generic boundary between 1 million people and space. That material assessment can include some substances the station already needs for other reasons. Materials made from low atomic number elements, including water and polyethylene, can be helpful under many radiation conditions. That does not make either one a complete answer, because the result still depends on the radiation environment and on how the material responds to it. It does mean that protection does not always have to begin with a separate layer whose only job is to stand between people and incoming radiation. Water is a clear example because a settlement of 1 million people would already have to keep a large water inventory moving through its life support system. Some of that stored water could be placed around occupied areas, allowing the same mass to belong in both the water ledger and the shielding ledger. The material would still be available to the city, rather than locked forever inside a dedicated wall. For a station where every delivered mass has to be accounted for, sharing those roles can make a design option easier to carry. But those two ledgers would then be connected. Water protects a particular area only while it remains in the place and arrangement on which that protection depends. If the settlement moves it to another reservoir, sends it through a different part of the life support system, or draws heavily on the store during an emergency, The geometry around that occupied area changes. The water has not vanished from the station, yet it may no longer sit where the protection plan expected it to be. A reserve assigned to a shelter would therefore need operating rules that preserve its position or account for the change in protection when it moves. That turns inventory management into part of radiation management. A protected compartment could not be evaluated from the station's total amount of water alone. Its local arrangement would have to be considered as the city used and redistributed that water. The approved evidence does not tell us how much should surround any room, what layout would protect a settlement of this size, or how far an emergency drawdown could safely go. Those answers require a stated mission environment and protection target, followed by a design that keeps the promised material in the required configuration when people need it most. The protection target has to be just as specific as the arrangement of the shielding. One published deep space analysis did this by stating the material, the mission, the intended dose, and the geometry used in its calculations. Those details were part of the result. Within that bounded study, the reported launch case met its stated target for 130 days. That gives engineers a concrete result to examine, but the duration belongs with the assumptions that produced it. It does not say that the same material would protect a permanent settlement, or that its dose target should become the target for a city with a different mission. Extending the stay changes the question. The particle environment matters as well. Radiation does not arrive as one uniform stream that every material reduces in the same way. The incident spectrum describes the particles reaching the shield and the energies they carry. As those particles pass into matter, their interactions alter how radiation is transported through the material. The biological dose behind the shield therefore depends on both what arrives and what happens inside the shielding, rather than on mass alone. Geometry connects those effects to the people inside. A mass placed around one defined space has a particular relationship to the incoming radiation and the protected volume. Spread that mass across a much larger habitat, change the shape or substitute another material, and the original result no longer describes the same physical case. You would need a new analysis with a new geometry, material, particle spectrum, mission duration, and dose target stated together. So the published mass result is evidence for a method of specification, not a citywide quantity waiting to be multiplied. It shows why a shielding number must carry its mission with it. For this station, permanent residence would require its own protection target and a design evaluated in the relevant particle environment. The deep space study does not supply either one, and treating its 130-day launch case as permanent habitat protection would claim more than the analysis established. Even that properly bounded radiation calculation would answer only the particle dose problem. It would not tell us whether the same structure could survive a physical impact, where the threat is momentum striking the station rather than dose accumulating inside a body. That difference changes what protection has to do. A radiation shield is chosen to reduce the particle dose reaching people inside. Protection from debris and micrometeoroids has to deal with small pieces of matter arriving at very high speed, where the event is sudden and concentrated at the point of contact. Whipple-style shielding addresses selected small impactors by placing a protective layer away from the station's pressure wall. When a suitable small object hits that outer layer at hypervelocity, the collision disrupts it before the remains reach the structure behind it. Its material and impact energy are spread across a wider area, giving the layers behind the outer shield a better chance of containing the strike. But that describes a particular protective method, not armor against every object the station might meet. The card supports no universal shield design and no promise of immunity from penetration. A layer selected for small hypervelocity impactors cannot simply be treated as proof that the whole habitat is safe from any collision. Larger objects that have been catalogued call for a different response. They must be monitored so their paths can be compared with the station's path, and the danger has to be handled through avoidance rather than left entirely to the hull. That does not establish a debris-safe orbit or prove that a station of this scale could perform any required maneuver. It establishes the division of work. Selected small threats can be disrupted by physical layers, while known larger threats require observation and an avoidance decision. Some strikes will still exceed the protection at one point, or reach a place where the layers do not contain the damage perfectly. At that moment, survival depends on what happens inside the habitat. The affected area has to be isolated from the environmental systems and spaces around it, so a local breach or damaged section does not turn into a wider loss of habitable space. The shell, then, belongs to an impact response system that also watches what is approaching and limits what a successful strike can reach. External damage may force an internal section to be cut off for a city-sized habitat that leaves a practical problem beyond the wall itself, where the people and essential services can still reach where they need to go when one route or one part of the station is no longer available. Cutting off a damaged section only works if the station can keep moving people and essential services around it. The inhabited area, therefore, needs more than homes and the systems that support them. Some of that area has to be reserved for circulation, freight, maintenance access, emergency response, and the other civic work that lets a settlement operate. A room on the plan does not add much usable capacity if the people or supplies meant for it cannot reliably get there. That makes every corridor part of an access commitment. Food and replacement equipment have to reach the places where they are used. A medical response cannot depend on a path that becomes unavailable at the same moment someone needs help. Maintenance may close a passage while workers repair equipment or isolate damage, even when the rest of the station remains inhabited. Disabled residents also need routes they can use. These demands turn movement space into part of the settlement itself, rather than whatever space happens to remain between dwellings. The network has to carry different kinds of movement without assuming that all of them can wait. Residents may be able to change a trip, while a repair crew, a freight movement, or a medical response may have less freedom. When one section is closed, another route has to preserve access to the places that still function. This does not tell us how wide a corridor should be, how many passengers a vehicle could carry, or how long any trip would take. It tells us what the city ledger must include before interior area can count as workable city capacity. There is another condition if a route passes between a rotating part of the habitat and a part that does not rotate. The motion environment changes along that route, so the crossing cannot be treated as though it were simply another level passage. Rotation is a design variable for the settlement, and access remains a requirement on both sides. Any proposed connection would have to account for those together. That is a systems requirement, not a transit design. It does not prove a particular hub, dock, vehicle, crossing method, speed or commute time. It does mean that movement competes for planned space from the beginning. The station's inhabited volume becomes usable only where care, cargo, maintenance, and people can still reach it when the most convenient path is closed. The most convenient path may be closed because the space around it is no longer safe to enter. A pressure loss or contamination event does not have to define conditions throughout the entire inhabited volume. Compartment boundaries allow the affected section to be isolated. That keeps a local event local, but it also removes every passage that crosses the sealed area from the usable network. At that point, access is no longer mainly about making a routine trip short. People on either side still need a reachable place to wait. Critical work still needs a way to continue, and supplies still need a route around the unavailable section. A path that works only while every compartment remains open cannot provide that kind of recovery. The remaining network has to connect people, cargo, and safe temporary locations without depending on the part that has just been isolated. Those alternate paths, refuges, and cargo approaches have to be reserved before housing fills the available surface. You cannot assign the same strip of the station entirely to homes and also count it as open recovery capacity. Once construction has consumed it, drawing a second route on a plan does not create the physical passage, protected space, or cargo access that the route requires. Recoverability therefore takes up real room, even on days when nothing has failed. Packing homes and workplaces more closely can shorten some daily journeys. Yet density can also push more movement through fewer junctions. If one of those junctions lies inside an isolated section, several apparently separate trips may disappear together. A compact layout may look well connected during normal operation while still depending on a single crossing. Short distance alone does not provide alternate access. The routes must remain separate enough that one sectional failure does not remove them all. This does not establish how many alternate routes a million-person habitat would need, how large its refuges should be, how quickly people could move, or how much cargo a surviving path could carry. There is no demonstrated evacuation doctrine or emergency performance standard here. The supported constraint is narrower. Sectional isolation is part of a habitation system, so reachability during that isolation has to be designed into the settlement. Only then can a closed section remain a local problem, while care, supplies, and essential work move around it. The routes that carry people and supplies also carry contaminants, and closing a route can only contain what has been detected. The same problem appears inside every recovery system. Keeping nearly all of a material is one result. Returning it in a condition that people can safely use is another. For habitat air, ISO 16726 treats harmful chemical contaminants as a controlled environmental requirement. A spacecraft has not solved its air problem simply because the atmosphere stayed inside its walls. Meeting that requirement calls for contaminant removal systems and monitoring. Air passes back into occupied rooms, so the system has to remove unwanted chemicals and measure the condition of what it returns. The measurement is part of recovery because it tells the operators whether the cleaned stream still falls within the required condition. Without that check, a large recovered quantity says how much air remained available, but not whether that air is acceptable to breathe again. NASA's Human Systems Standard places food, water, contaminants, waste, and habitability within coupled operational requirements. That coupling changes how we should read any recycling percentage. A stream leaving one process does not disappear into an abstract recycling total. It enters another service, where its composition and condition affect people, equipment, or both. Water returned for human use has to satisfy the specification for that use. Material recovered from waste has to satisfy whatever specification governs its next destination. You can see the distinction in a simple inventory. A store may recover almost every container sent to it, yet the count of recovered containers cannot tell you whether their contents are clean. Quantity answers how much came back. Quality answers whether it can go back into service. In a sealed habitat, both answers have to travel together, because an unusable output can accumulate even while the reported recovery fraction looks high. These standards do not provide contaminant limits for a city of 1 million people, a complete testing protocol for its recovery plants, or proof that all of its material streams can be closed. They support a narrower design rule. Before the settlement can decide how to collect, separate, or reuse a stream, it needs to define the condition that stream must meet when it returns. Only then does a recovery percentage describe usable material, rather than material that has merely been captured. That return condition immediately divides the station's discarded material into separate streams. NASA's Human Systems Standard treats food, water, contaminants, waste, and habitability as coupled requirements. A discarded item can cross several parts of the life support system. The station also has to ask where it has been, what it contains, how it affects the living environment, and what condition the next process requires. Packaging, spent filter media, toxic contaminants, food residues, biological waste, and worn machinery are planning examples, not a complete waste list for a city of 1 million. They cannot be treated as though they share one composition or one suitable destination. A filter has been used to remove something from another stream, so the captured material remains part of the handling problem. Food residue and biological waste enter the habitat's cleanliness and contamination controls. Worn machinery may still contain material worth recovering, but that does not make it suitable for the same route as packaging. The label "discarded" tells the operators almost nothing about what should happen next. Sorting is therefore part of the recovery system itself. If unlike streams are combined too early, one can change the quality of another before either reaches treatment. Keeping them apart preserves the chance to test each output against the specification for its intended destination. That destination may be the stream's former use, but it may instead be a different use with different requirements. Controlled contaminant removal supports this kind of separation. It does not support sending every output back into circulation without regard to what remains in it. Some material will not meet the condition required for its former role. The station must then separate and treat it for another use, hold it in storage, or replace the lost function with new stock. None of those choices makes the material disappear. A treatment route needs equipment and handling. Storage occupies managed space and leaves the material in the settlement's inventory. Replacement draws down whatever reserve can provide the missing item or substance. On Earth, rejected material can leave a building and enter an outside waste system. This habitat has no routine outside destination. Every rejected output remains an internal task until a safe next use, a treatment path, or a storage decision has been assigned. The recycling symbol has become a chain of linked processes, with each usable stream protected from the streams that do not match it. One possible destination is a biological treatment system, though that name can make the process sound simpler than it is. The European Space Agency's MELISA concept approaches regenerative life support as a set of separate, linked compartments. Material does not enter one living machine and emerge as everything the settlement needs. It passes through distinct stages, with each compartment doing a particular kind of work before handing its output onward. Those handoffs connect several services that would otherwise look separate. In the MELISA concept, processing waste and carbon dioxide is coupled to the regeneration of food, water, and oxygen. A material that leaves one service as waste may therefore become part of the input to another service, while carbon removed from the air can enter biological production. Treatment sits between the habitat's sanitation, atmosphere, water supply, and food system, so a change in one flow can reach more than one destination. Photobioreactor research shows the same kind of connection at a smaller and more specific level. A biological reactor can contribute to waste processing and water treatment, while photosynthetic organisms help revitalize the air and produce edible biomass. That gives one biological stage a place in several recovery loops, but it does not erase the boundaries between those loops. The material leaving the reactor still has to be suitable for whatever receives it, and the reactor itself has to remain within the conditions its organisms can tolerate. So the handoff carries more than matter. It also carries the result of the previous stage's operating state. If a compartment changes the composition or condition of its output, the next compartment receives that change as part of its own input. A chain like this has to be managed stage by stage, because successful processing in one compartment is only valuable when the following compartment can use what arrives. MELISA is a life support concept, and photobioreactor work establishes research pathways with biological constraints. Neither demonstrates a fully closed city in space, an autonomous ecology that regulates itself, or a system that can feed an entire human population for generations. What they establish is the engineering shape of biological recovery. Linked processes can join air, water, waste, and food functions, but every link depends on the condition passed forward. Once living processes become part of the city's machinery, variation inside any one of them can move along the chain. That variation does not begin only when something breaks. A photobioreactor can remain physically present, with its vessels and connections still installed, while the organisms inside respond to a change in their surroundings. Microbes do the same. Their performance depends on environmental and process conditions, so the state of the biology cannot be read from the existence of the hardware around it. That makes the output more complicated than a stream that is either flowing or stopped. Gas moving between a liquid and the space above it can affect how the process behaves. Food safety can also decide whether material produced by a biological stage is fit for its intended use. In either case, the stage may still be operating, yet what leaves it may no longer provide the condition that the following service was designed to receive. Suppose that stage supplies part of an air, water, food, or waste function. A change inside it then changes the input presented to whatever comes next. The downstream equipment has not necessarily failed, but it is now being asked to work with something different. The source of the trouble and the place where its consequence appears may be separate parts of the chain. That consequence follows from the linked process architecture. Once one service uses another service's output, a local biological change can travel beyond the vessel where it began. The city therefore has to treat biological performance as an operating state, something that can shift while pumps, pipes, and chambers remain in place. Interdependence is still valuable because one process can supply material needed by another. The same connection also carries variation forward. A process chain built from living stages is dynamic in a way that a diagram of installed equipment cannot capture. The available work supports that dependence on operating conditions, gas and liquid behavior, and food safety constraints. It does not tell us which sensors a space city would use, how quickly a change would be detected, how often a biological stage would drift, or how an ecology at that scale would recover. Those questions remain open. What the linked evidence does establish is the added maintenance burden. Operators must know when a biological output has changed enough that the next service can no longer use it as expected, even though every major piece of hardware is still there. When a sensor, filter, or other piece of equipment needs attention, the repair may depend on a small physical item. On Earth, that item can come from a warehouse or a supplier. In orbit, waiting for delivery makes the distance part of the maintenance problem. Yet the International Space Station has already shown that delivery is not the only possible answer for every item. NASA describes the station's additive manufacturing facility as a way to make selected tools and components on demand in orbit. That wording matters because it gives the capability a clear edge. The facility can produce selected items, and NASA does not claim that it can produce every replacement a large habitat might need. Within that selected scope, though, this is real production where the finished item will be used. It is operating hardware on the International Space Station rather than a proposal for a future space city. For a repair that falls inside the demonstrated scope, the immediate logistics question changes. Instead of asking only when the needed item can arrive from Earth, the crew can first ask whether it is one of the items that can be made locally. If the answer is yes, the useful object can be produced in orbit, close to the equipment that needs it. The capability does not erase the repair problem. It changes one step in the response from transport to local manufacture. That is a limited change, but a concrete one. A closed system will still need people to notice a fault, identify what has failed, and decide what physical item is required. Additive manufacturing adds another possible route after that diagnosis. Some needs may remain delivery problems. A selected need may become a production decision instead. The boundary is just as important as the capability. The station facility demonstrates on-demand manufacture of selected tools and components. It does not demonstrate that one printer can make all the parts required by a habitat for 1 million people. And it does not establish that such a habitat could supply itself. Calling the machine a factory would blur the difference between producing a defined item and sustaining an entire settlement. Even when the printed item solves the immediate repair, its existence still rests on material and industrial support deeper than the finished object in the crew member's hand. That deeper support begins with the material fed into the machine. An additive manufacturing system can produce only items its process, equipment, and feedstock allow. If the material is missing, the station lacks the required process, or the equipment is out of calibration, a fabrication tool does not make the replacement available. On-demand production moves some inventory from finished parts into raw material and production capacity, but those supplies and capabilities still have to exist. The digital design carries another dependency. A file may describe a shape, yet a replacement needs a qualified design, one trusted for its assigned function when made by the selected process. Changing the material or production method can change the question being asked. The station needs more than instructions telling a machine where to place material. It needs a basis for treating the result as the required part. Inspection connects that design to the object that comes out. The crew needs some way to decide whether the produced item meets the function for which it was intended. A piece that looks complete may still require evidence before it can be installed in a system whose failure could matter. The exact inspection method is not defined by the on-orbit manufacturing example, but the dependency remains. Production alone cannot certify its own result. Then the chain runs behind the production step. Software must remain usable, tools must be available, and skilled people must know how to operate the process and interpret what inspection finds. The calibrated machine can also wear, fail, or require adjustment. Maintaining it may demand other tools and machines, along with people who can diagnose the fault. A station that can make a replacement part today may lose that ability if it cannot repair the equipment that makes the part tomorrow. This is a systems inference, not a measured list of the minimum factory a settlement would need. The available evidence does not establish the required industrial depth, manufacturing mix, inventory, or energy demand for a million-person station, and it does not show that such a station could provide them independently. It shows why the planning object has to widen. A spare is supported by material, equipment, design knowledge, inspection, software, labor, and maintenance capacity. Before the repaired system returns to service, that whole chain must provide a reason to trust it. Making the replacement is therefore only part of the repair. NASA's human system standards describe a spaceflight habitat through requirements that continue while people live and work inside it. The condition of the vehicle remains tied to human health and performance after the hardware has been delivered. Safe habitation is an ongoing demand placed on the working station, not a label earned once when the station leaves its builder. That changes what it means to put a repaired system back into service. If the system carries a life-critical function, a replacement component cannot be trusted because it fits, powers on, or resembles the part it replaced. The required function has to be restored, and the station needs evidence that the replacement has restored it before the repair can be accepted as safe. This need for testing and acceptance is a systems inference from NASA's continuing requirements frame. The source does not give us a certification regime or a sequence of tests for a million-person habitat. It does not tell us how many people would do the work, how reliable their repairs would be, or whether every repair could be qualified inside the station. Those details remain unresolved. But the consequence is clear. Inspection has to establish the condition of the replacement and the system around it. Diagnostics have to help operators distinguish the failed item from a deeper fault that could damage the new one. Testing, then, has to show that the life-critical function has actually returned. Acceptance is the decision that this evidence is good enough for the system to carry its duty again. Documentation keeps that evidence available after the people who performed the work have moved on. A later operator needs to know what failed, what was changed, what the diagnostics showed, and what condition was accepted. Without that record, the next repair begins with missing knowledge. The crew may be able to exchange another item, yet still be unable to establish why the system failed or whether its function is safe. So the industrial chain must return more than an object. It must return an object whose condition and fit for service can be established within a habitat that cannot casually send its failures to an outside maintenance network. That turns repair into verified restoration, supported by people who can preserve the knowledge, judgment, and authority needed to trust the system over time. That trust also depends on the condition of the people doing the work. Long-duration spaceflight research identifies physiological limits and health risks that continue while people remain in space. A permanent habitat cannot treat human health as a problem solved when the structure is finished. The operators who inspect a repaired system read its diagnostics and decide whether it can return to service are living inside the same environment they are responsible for maintaining. Medical knowledge, therefore, has to remain available as a working capability. Health must be monitored over time, changes must be recognized, and appropriate countermeasures must continue rather than being treated as supplies used once at the beginning. This does not tell us how healthy a population of 1 million would be or predict the condition of people born in the habitat. It tells us something narrower. Long residence leaves continuing human constraints, and the city needs people and procedures able to respond to them. The same dependency runs through the maintenance system. Training has to prepare someone to understand the equipment, carry out an inspection, and recognize when a result falls outside an accepted condition. Staffing has to leave qualified people available when monitoring finds trouble or a failure demands recovery work. Inspection authority has to be clear enough that a questionable machine is not returned to service merely because the habitat needs it. Recovery procedures must preserve what to do when normal operation has already broken down. You can stock a workshop with tools, materials, and replacement parts, but those resources stay usable only while people retain the knowledge to choose and test them. That knowledge cannot sit only in an archive. Someone must be trained to apply it to the machine in front of them, while someone else keeps watch over the health of the operator and the conditions around the repair. Safe habitation remains an ongoing operation, not a property built permanently into the shell. None of this provides a staffing ratio, a system of government, or a promise that knowledge will survive across generations. A review of long-duration health risks cannot answer those civic questions. It does show why industrial depth includes human capacity. Machines and stored material can support a city only while competent people can monitor health, inspect equipment, preserve working knowledge, and recover from failures without losing the ability to do the same work again. That architecture cannot be chosen from the population alone. 1 million residents may be fixed, while nearly every burden around them changes with the kind of station being built. Start with rotation. Artificial gravity couples the station's radius to its spin rate, so choosing one changes the other. A smaller rotating home must spin faster to produce the selected gravity. A larger one can turn more slowly. That decision changes the curve of the inhabited ground, how conditions vary between the floor and the axis, and the structural problem created by a city moving around its center. Food brings a different commitment. If the station is meant to grow a complete human diet, then cultivated surface becomes part of its physical scale, and biological life support becomes part of its daily operation. Choose another food model, and that cultivated burden does not simply disappear. It moves into whatever supply, storage, processing, or production arrangement replaces it. The population figure stays the same, but the system carrying its diet is different. Orbit changes the environment the station must endure, while the shielding strategy determines how much of that exposure is handled by location, material, or another protective choice. Power belongs on its own ledger. The selected source must support continuous demand, and its waste heat must still be rejected. Industrial depth answers a separate question. When a pump, seal, control system, or larger machine fails, how much of its replacement can the settlement make for itself? A deep industrial base asks for more equipment, materials, skills, and internal production, but a shallow one leaves more dependence outside the station. These choices also meet one another. A wider rotating structure changes the amount of structure that must be built and protected. A complete diet farm adds biological systems that need energy, heat control, maintenance, and replacement parts. Greater industrial depth may improve repair capacity while adding machinery that draws power and releases heat. The available sources support those relationships, but they do not supply a finished integrated design or prove that any one branch can house 1 million people. They let us compare declared architectures until radius, spin, food, orbit, shielding, power, and industrial depth are specified. Ranking the ledgers would compare stations that have never been made into the same station. Choose to grow a complete diet inside the station, and the food system shapes the design. Ground studies place the highlight crop area for a complete diet at roughly 40 to 50 square meters per person. For 1 million residents, that becomes 40 million to 50 million square meters of cultivated area. The estimate does not predict the exact size of an orbital farm, because a ground study cannot settle the crops, yields, growing methods, or losses of a future station. It does show the scale of that choice. Farming has become a city-scale allocation of productive surface. That surface cannot operate as a garden beside a separate life support system. Crops take up water and carbon dioxide, release oxygen, draw nutrients from circulating material, and produce biological matter that has to remain under control. Food production, therefore, becomes part of the station's water handling, atmosphere management, nutrient circulation, and sanitation. A failure in one system can reach the others, Biological processes also vary, so maintaining a complete diet requires monitoring and control, rather than treating every harvest as a fixed mechanical output. The sources support these connections, though they do not prove that anyone has built a closed ecosystem able to feed a city of this size. The farm also needs sustained electrical service. Highlight crops need light whenever sunlight is unavailable or cannot be delivered in the required amount, while pumps, air movement, processing, and control equipment add continuous loads. The evidence here does not provide a universal power figure for the city, so assigning one would pretend that all farm designs are alike. The physical consequence is firmer. Electrical energy used inside the habitat ultimately appears as heat, and sustained heat has to leave by radiation. More farming power therefore means more thermal energy for the station to export. That does not give us a universal radiator size, since the answer depends on the chosen power system, temperatures, and farm arrangement. It does bind the decisions together. Internal food independence commits the habitat to a large cultivated surface, reliable biological control, continuous power, and enough heat rejection capacity to keep them running. Farming is not ruled out, and imported food is not declared better. This architecture simply concentrates its burden in surface, power continuity, and thermal export, while another choice could move the leading pressure elsewhere. Move the city into a harsher radiation environment, and its burden shifts. The shield cannot be chosen from population alone, because its performance depends on what radiation arrives, how much dose the design permits, how long people remain exposed, and which material surrounds them. Geometry changes the result too. A compact habitat with protected rooms presents a different problem from a structure whose living areas sit close to its outer surface. Until the mission and habitat design are defined, there is no single shield thickness or mass to assign. That protective mass answers only part of the danger outside. Debris can still strike a pressurized habitat, so protection also depends on seeing hazards early enough to respond, avoiding what can be avoided, and limiting the damage when an impact happens. The structure may need to localize a breach and isolate the affected area before lost pressure spreads the emergency. A shield and a debris response, therefore, do different jobs. The available evidence supports those separate functions, but it does not supply an impact rate or a complete strategy that guarantees safety. Damage then meets the settlement's industrial limits. A city with shallow manufacturing may be able to make some parts while still depending on stored spares, suitable feedstock, qualified machinery, and inspection equipment. Producing something with the right shape is not always enough. A replacement must also be checked well enough to trust inside a life support system or pressure wall. Skilled people have to operate that chain, diagnose failures, and decide whether a repaired component can return to service. Those people are part of the repair capacity. They need training, time, safe working conditions, and enough physical and mental health to keep doing demanding work as wear accumulates. Yet the sources do not define a minimum industrial depth, a staffing pattern, or a repair system proven reliable across generations. They show the dependencies, not the precise line at which a settlement becomes self-sufficient. In this branch, protective mass, habitat geometry, damage isolation, and replacement capacity can press harder than cultivated area. A serious strike or a worn critical component can remain a supply chain problem even when the farms are performing well. That does not prove protection or manufacturing must fail first. It shows why a 1 million-person station can have a different leading constraint when exposure is high and its ability to restore critical systems is shallow. No approved source gives us a complete orbital city of 1 million people that has been kept running without interruption. There is no direct operational counterpart in which farms, power, cooling, shielding, medicine, manufacturing, and repair have all worked together at that population for long enough to validate the whole city-scale settlement. We can examine each dependency, but we cannot point to a finished example and say the integration has already survived real use. The separate physical relations still let us discuss designs conditionally. Rotation connects a habitat's size and spin to the artificial gravity its residents would feel. Crop evidence constrains how much cultivated area a food system may need. Energy use creates power demand and waste heat that must be removed, while radiation protection depends on shielding and the exposure allowed by a chosen location and structure. Those relations can shape a proposed architecture. They do not show that one complete architecture has been built, medically accepted, or proven feasible. Reducing the remaining uncertainty would take several kinds of work because each answers a different question. An architecture-specific integrated model could test whether its mass, energy, heat, food, and repair accounts close together. Long-duration rotation research could narrow the medical uncertainty around people living under the selected spin conditions. Pilot ecosystems could show how food production and recycling behave through disruptions rather than during a short demonstration. Materials tests could expose wear and damage, while maintenance records from sustained operation could show whether crews and machines can keep replacing what fails. No single test would certify the city. So the evidence does not support declaring 1 million people safe in a single orbital settlement today. It also does not identify a physical law that forbids every declared architecture. 1 million people might live there only if their city operates as a maintained industrial ecology, continually growing food, rejecting heat, limiting exposure, and restoring its own critical systems. Which account fails first would depend on the actual design, its rotation, location, shielding, farms, power system, materials, and depth of repair. That makes the answer conditional. It is neither a simple no nor a construction-ready yes, because permission from physics is not proof of engineering, medical, economic, political, social, or operational success.